हेलो फ्रेंड्स, तो आज हमारा सेशन है सॉलिड स्टेट और सरफेस केमिस्ट्री के बारे में। आज इन चीज़ों का रिवीजन करेंगे हम। ये दोनों बहुत ही छोटे चैप्टर्स हैं और काफ़ी इम्पोर्टेंट भी हैं। सॉलिड स्टेट काफ़ी क्वेश्चंस जो आते हैं इसमें से, और सरफेस केमिस्ट्री थ्योरी के हिसाब से काफ़ी इम्पोर्टेंट है। तो हम सबसे पहले सॉलिड स्टेट से शुरू कर देते हैं। तो अब आप यूनिट सेल्स के बारे में तो जानते ही हैं, करेक्ट। जो लैटिस, हमने लैटिस के बारे में पढ़ा है। सबसे इम्पोर्टेंट चीज़ लैटिस क्या होता है। बेसिकली जो एटम्स होते हैं उनके अरेंजमेंट को हम लैटिस स्ट्रक्चर फॉर्म बोलते हैं। और उस लैटिस के अंदर एक सेल को जिसके अंदर हम जो कैलकुलेशंस होती हैं, बेसिकली क्यूबिक सेल को यूनिट सेल कहते हैं, राइट। अब ये जो यूनिट सेल्स हैं वो कुछ उनके जो स्ट्रक्चर्स होते हैं अलग अलग तरह के होते हैं। जैसे कि हमारे पास होता है एक सिंपल यूनिट सेल, ठीक है। हम इन सारे स्ट्रक्चर्स को देख भी लेंगे। तो हम बात कर रहे हैं ये देखें। तो जो हमने टाइप्स ऑफ यूनिट सेल्स पढ़े हैं उनको हम समझ लेते हैं। पहला होता है सिंपल यूनिट सेल या फिर प्रिमिटिव यूनिट सेल। अब इस प्रिमिटिव यूनिट सेल का इतना ही बेसिक है कि एक जो क्यूब है उसके कॉर्नर्स पे, सिर्फ और सिर्फ कॉर्नर्स पे आपके एटम्स प्रेजेंट होते हैं, करेक्ट, ठीक है। और ये एक दूसरे को टच कर सकते हैं। यह है आपका बेसिक प्रिमिटिव यूनिट सेल। सेकेंड होता है आपका BCC, बॉडी सेंटर्ड यूनिट सेल। जो बॉडी सेंटर्ड यूनिट सेल होते हैं उनमें क्या होता है, आपका जो प्रिमिटिव है वो तो है ही सही, और उसके अलावा उसके सेंटर में भी एक एटम लाई करता है, ठीक है। अब इसके अंदर इसकी खासियत क्या रहती है कि सारे के सारे जो एटम्स होते हैं वो कॉर्नर वाले एटम्स एक दूसरे को टच नहीं कर सकते। सिर्फ और सिर्फ जो टच करेंगे एटम को वो कौन सा होगा, सेंटर एटम। तो सारे के सारे कॉर्नर के एटम सेंटर के एटम को, जो बॉडी के सेंटर में है, बॉडी के सेंटर मतलब एकदम बीचों बीच। तो आपने एक क्यूब लिया, क्यूब के कॉर्नर्स पे आपने 8 एटम्स लगा दिए और उनके एग्जैक्ट बीच में एक और एटम लगा दिया, और वो कहलाएगा हमारा BCC, बॉडी सेंटर्ड क्यूबिक सेल यूनिट सेल। All right, okay, so we know what primitive is only at the corners, whereas in the body centered we have at the center of the body too. All right, so the number of thirdly we have face centered cubic cell. What we have in face centered is, this is a face centered cubic cell. So what we have in this is that we have we have this 8 atoms present at the corner, and in addition to that we have the atoms present at the face center. What is the face of a cube? The basically when you see a Rubik's cube, so the colors that you're seeing on the sides are the faces of the cube. So the center of that Rubik's cube, the center of the faces of the Rubik's cube, that will be this side 1, this is 2, this is 3, this is 4, this is 5, and behind will be 6. Alright, so this 6 will be at the face centers, and hence this is called a face centered cubic cell. These are the 3 primitive ones. There are 3 important ones. Alright, so the primitive one, the simple, has only total number of atom, only one total number of atom in its unit cell. Now how do we calculate that? So uske liye what we do is we see the contribution. So the contribution of an atom present at the corner is 1/8, right? So at the corner the contribution is 1/8, whereas on the face the contribution will be half, and if it's inside the body then the contribution will be complete one. Hence जो simple होता है, the simple cubic cell will have a coordination number of will have total number of 1 atoms in its unit cell, whereas the body centered will have total number of 2 atoms. How? 1 from all the 8 atoms present at the corner, 8 into 1 by 8, 1, and 1 because of the body centered. If you talk about FCC, so we have 4 atoms present inside a unit cell. How? So we have 8 present at the corners, the contribution will be 1. We have total 6 present at the face centers and the contribution is half. So 1 plus 3. Correct? Hence it gives us 4. 4 for face centered, 2 for body centered, and 1 for simple. Now, out of these 3, the most important one is FCC. Now, how can I say that this one is important, the others are not important? Now, this you have to remember. Face centered is a very stable configuration unit of the unit cell. Why? Because of its high atomic packing fraction. Atomic packing fraction क्या होता है? What is atomic packing fraction? So basically, what we are talking about is atomic packing fraction. I'll tell you the formula. Remember how when you're passing all the classes, so when you want to take out percentages, what you do? You say the marks that you have got upon the total number of marks into 100. Correct? Same is the packing fraction. What you want to calculate is that how much of the unit cell is packed with atoms. Now, the unit cell is cubic. Correct? Whereas the atoms present are circular. They are in the spherical shape. So they can't completely pack the unit cell, right? So what happens is, so atomic packing fraction is basically, how much percentage is occupied. So total volume occupied by atoms upon volume of unit cell, correct, into 100. So this is your atomic packing fraction. इसको हम, now we know that volume of the atoms will be 4 by 3 pi r cube. R is the radius of the atom. Now there can be more than one present in the atom present in the unit cell. So n is the number of atoms present in the unit cell. Total number of atoms present in the unit cell. All right. So n into 4 by 3 pi r cube upon a cube, where a is the edge length of the unit cell. So this is your formula for packing fraction. So now when we are talking about that, FCC is the most stable configuration for a unit cell. Why? Because of the highest packing fraction. So let us see how much packing fraction each of them has. So the primitive, the simple one, has 52%. The BCC has 68%, whereas the FCC has a 72% packing fraction. And the greater the packing fraction, then more number of atoms present in the unit cell and higher is its stability. Alright. अब इसके अलावा we have 2 more different types of unit cells, alright, for you to remember. They can or cannot come in the exam, the competitive exams, but they are important for the competitive exams. The CBSE, they might or might not come. So the 2 are end-centered and hexagonal. So end-centered is basically nothing but similar like face-centered, but only 2 atoms up on the opposite faces. Like we have 8 at the corner, as you can see, and only 2 atoms present on any of the opposite face. अब ये up down भी हो सकता है, left right भी हो सकता है, और ये front और back भी हो सकता है. Any of the 2 faces. So this is known as end centered. And how many atoms present in this end centered? So one from the corners and one from the opposite faces. Total 2 atoms present. Alright. So इसका भी packing fraction कितना होगा? 68%, just like body centered, which is lesser. The next one, which is hexagonal unit cell. This hexagonal unit cell is quite an important. So what it has is, generally we have a unit cell as a cubic unit cell, but this hexagonal unit cell has a hexagon as a unit cell. So the total, obviously, how many atoms will be present in this? Total number of atoms will be 6. How? So the 6 present in the upper corners, upper edges, they will contribute 1/6. The 6 present in the lower edges will have 1/6 contribution. So this goes to 1, this goes to 1. Alright. So 1 at the faces or top and bottom, they will contribute half each. So half into 2 is again 1. We got 1 plus 1 plus 1, total 3 atoms, and these 3 atoms are present inside the body, so the total contribution is complete. Hence total 6 atoms are present in the hexagonal unit cell. Alright. Now this hexagonal unit cell and the FCC unit cell, they both have equal packing fraction of approximately 72%. Hence they both are equally efficient, and hence the maximum structures that are found are present mostly in the face centered unit cell or in the hexagonal type of unit cell. Alright, this is easy to understand, right? So why do we have equally efficient closed packing? Let us understand that too. Although the coordination number here is 4, although the total number of atoms present here is 4, and although the atoms are present here is 6, still they have equal packing fraction. That is because of the volume that is in the denominator. Here the volume is for the cube, whereas here the volume is for the hexagonal. Hence both things are changing, the numerator and the denominator. Hence they approximately come out to be 72 to 74%. Hence they both are equally efficient. Okay. So this was about the unit cells, the types of unit cells. Now talking about the one more thing important in these two. So yeah, we have seen the structures. I'll just talk about the important stuff. Now this is very important from the exam point of view. Now we have FCC and we have HCP, the hexagonal closed packing and the face centered closed packing. The face centered closed packing has a ABC type arrangement. Sorry, the face centered closed packing has a ABC type arrangement. We'll see ये होता क्या है. And HCP has a AB type arrangement. Now let us understand what this is. So this A, B and C, these are the layers of atoms which are identical. So if I say A, so A is one layer of atom. Alright. Whereas B is another layer of atom which is not identical to A, and C is another type of layer which is not identical to either A or B. Again, if you talk about A, it's the same layer as the first one. So I'm just talking about these layers just like this. But let's say this is one layer, this is another layer which is different. These are not papers right now. And this is another layer which is again different. तो अगर आपका ये A है, alright, और इसके ऊपर this B is placed in some way, and then the C is placed in some other way. So now these kind of arrangements are seen in FCC. ठीक है. Now on the contrary, if you check for HCP, the hexagonal one, what you will observe is only AB layer type of arrangement. So one is A, then there is B, and then there is again A, then there is again B. So the arrangement is alternative. Hence every alternate layer 1 leave one and then again one is exactly same. Whereas in cubic, every fourth layer will come out to be the same. In hexagonal, every third layer is same. A, B, A, B, A, B. So the third layer is similar to the first layer. Whereas in the cubic FCC, the fourth layer A, B, C, A, B, C, the fourth is similar to the first layer. How to remember this? Just from the exam point of view, if we talk, how just to memorize this, I'll give you a very short trick. So we know that cubic closed packing, right? Cubic means 4. 4 means the fourth layer. ABC, ABC, ABC. You can remember this, and the other one is directly to the hexagonal. So ABC is to the cubic, whereas AB is to the hexagonal. Don't remember the diagrams. Please note this down. Don't remember the diagrams. Rather important is to remember this kind of arrangement that is present in this kind of cells. So this is an important kind of thing, and this is an important formula. Please remember these kind of stuff. All right. Moving on further, we'll be talking about, so these, now whatever we saw in this arrangements here, these arrangements, so these are all same type of atoms. They are not two different atoms. These are all same atoms present in one unit cell. Alright, and hence this is called a unit cell. In a unit cell, only one type of atoms are present. Alright, hence this is called a unit cell. Now, talking about the more important thing in the unit cell, which is the voids. Now don't compare these voids as the void in the space. All right, this voids are present in the inside the unit cell. They are present between the atoms. I know atoms are very small. You can't understand exactly how they would look like, but we can at least understand. All right, from these structures that scientists have found through different processes. All right, let's check out what different kind of voids are. So the main important voids that we see and study in our classes is tetrahedral and octahedral voids. How they are made? Very simple. Let us see. So what we see here is this top. This is the top view. Here is the side view, and here is a simplistic diagram of the arrangement. So I'll make you understand with the side view. So what this tetrahedral void is, basically a void between a layer of one atoms. See, you see 3 atoms present. So these are like 1, 2 and 3 atoms present. And on top of it, if you put a 4th atom, so the space that is left in between these 4 atoms is known as tetrahedral voids. This, you can compare this void to as if you know the structure of methane. So all these 4 hydrogens, if these 4 hydrogens are present at the tetrahedral points, correct, and the carbon is present at the center, if I take the carbon out, what will be left there will be the void. That will be the tetrahedral void. This one. So here is one, here is another atom, here is a 3rd atom, and here is the 4th atom which is behind. So the void which is left here is the tetrahedral void. ये बात समझ में आ गई, clear है? So next is the octahedral void. What octahedral void is? Basically, we have a layer, and this layer, इसके ऊपर we have alternatively put the same layer on exactly ऊपर, just top of it. Same layer, we have just, what we have done is we have rotated it, and so what can I say? This is आपका one layer. Now this is its exact layer, but what if I rotate this layer and put it on the below layer? So at this point of time when the voids are formed, these voids are known as octahedral voids. Let's see. So these are the 3 atoms, and as उनको पूरा 180 rotate कर दिया, so these are the 3 other atoms. So due to the 6 atoms, the void which is created in between is known as octahedral voids. Why are these names tetrahedral and octahedral? That is because of the shapes. It forms a tetrahedron. The void looks like a tetrahedron actually. In here the void looks like a octahedron, and hence the names tetrahedral void and a octahedral void. So here are the top views. If you can understand these, not important again. All you have to remember is how they are present inside the atom. One more thing which is important to notice or to remember is basically the number of octahedral voids and tetrahedral voids present in the unit cell. So to understand that, we have a very simple formula. Total number of octahedral voids present in a unit cell will be exactly equal to the number of particles, the atoms present in the unit cell. Okay, this is clear. Now secondly, for the tetrahedral voids, if we talk about, so total number of tetrahedral voids is basically twice the number of atoms, the number of particles present in the unit cell. These two formulas are quite important. Octahedral number of particles जितने present होते हैं उसके बराबर होती है. ये octahedral voids की बात कर रहे हैं. Voids, tetrahedral voids, number of particles जितने भी होते हैं उसका double हो जाता है. Clear है? Okay. Now, if it next, and obviously there is never a one unit cell in a lattice. There are so many number of unit cells, so the voids will be multiple. Obviously they will be present. Next we'll talk about ionic crystals. So अभी तक जो हम बात कर रहे थे unit cells की, they were having same atom present everywhere, identical atom. Alright, right now what we are talking about is when more than one atom is present in a unit cell, then those are known as ionic crystals. Examples: sodium chloride, cesium chloride, the zinc blend, that is zinc sulfide, AgCl, KCl, as many examples you want, BeF2, as many examples you can make out of it. All the ionic forms of crystals which have more than one number of atoms, can be 3 or 4, 2, we are going to majorly talk about 2 atoms. Alright, so ionic crystals के अंदर what will have 2 basic atoms, will be cation and anion. ये तो आपको सबको पता ही है. So we know that generally the cationic ratio is greater than the anionic ratio, and due to this ratios, if we know the ratio of cation is to anion, then from that we can find out the radius ratio of the cation, the radius ratio of the anion, and even the edge length. What is the edge length basically? अभी तो जिसके बारे में हम discuss कर रहे थे. So how these atoms are present here, as here if one is present, then this other is present here, and then there will be a third one present in between, right? And this is the edge of the atom, of the unit cell. So what we know of the ionic crystal is Rc to Ra. This is called radius ratio. What is this called? Radius ratio. And this is very important. This is important for remembering point of view too, as direct questions can be asked from this kind of problems. So here are some radius ratios that occur for different types of crystals. So based on the radius ratios, we have different coordination numbers, the voids, and the examples. So what we are talking about here is that radius ratio of cation to anion. We know that the cation is generally bigger than the anion, hence the ratios are generally only less than 1. They are not more than 1. They are in the fraction less than 1. So if we have a radius ratio of less than 0.155, the coordination number is 2. The void is linear, and the example is beryllium fluoride. Similarly, we have, you can see as from the table, we have different types of radius ratios. So why are these in range? Because in this range there can be multiple examples and multiple types of crystals which can form in this radius ratios, and they will remain exactly of the same type when they are in the same range. What's important here is these three ranges. The above two generally questions are asked, but the very important ones are the tetrahedral and the octahedral voids that they create. Hence these two are major ones, and this one also is important. So you have to remember these, and the coordination numbers you obviously have studied. So the coordination numbers also you'll have to remember accordingly. Examples here देखिए आप, zinc blend, here it is zinc blend, here is sodium chloride, correct? Here we have cesium chloride. Please remember this. We'll keep coming back to this number, to this table again and again during our conversations. Alright, for now I'll remove this so that we can move forward. Alright, so let us also see some examples based on radius ratios ke. Alright, so these examples that we're talking about, here we have. So here we have some crystal structure types, lattices. Alright, here we have, first is rock salt, that is NaCl, right? NaCl, that is sodium chloride. So what we see here is it has an AB type of arrangement. What is an AB type of arrangement? That is what we talked about, FCC. That is why it has a AB type of arrangement. This AB here means 2 atoms, sorry. So this AB here means 2 atoms. Only 2 atoms we are talking about. Correct? Similarly, just as zinc blend is again AB type. For CaF2, the fluoride, we have AB2 type. Alright. And for anti-fluoride, if you talk about, there is A2B. It's exactly opposite to the structure. We'll come to the structures slowly. And the last is again cesium chloride type, which is a AB type. So let's talk about rock salt. So what we see in a rock salt, that is sodium chloride, is it has, if we have a lattice, when there are number of unit cells present, alright, what we're talking about is many, n number of unit cells present in the lattice. What we see is, these are the important things. The coordination number is 6. 6 for sodium and 6 for chloride. And the number of formula units per unit cell is 4. How do we arrive at this number? We'll understand in the process. So first thing first, NaCl is a FCC arrangement. It has an FCC arrangement where Cl minus, the N ions, are present at the edges. Alright, and the sodium ions are present at the voids and at the edge centers. So the FCC arrangement is made by whom? Chloride ions. Only chloride ions make the FCC arrangement. The sodium ions will go at the edge centers and at the voids. All right. So why do we have the coordination number as 6? Let us understand that. So here, let us imagine there is one Cl present at the coordinate. So next to it will be one sodium here, one sodium here, one sodium here. I'll make the sodium with another color. This is 1, this is 2, this is 3, this is 4. But these are only 4. Where are the other 2? Well, the other 2 will be present on the top and one on the bottom. So if this is the layer, chloride, then 1, 2, 3, 4 sodium ions, 5 at the top and 6 at the bottom. Hence the coordination number of every chloride ion is 6. And similarly we can say that sodium ion के लिए भी the coordination number is exactly 6. Now ये बात समझ में आ गई होगी. Next thing is to talk about their unit cell, the number of unit cell per formula, per अपना lattice. So what we see in a rock salt type structure, the NaCl structure is what we are looking at here. That we have 1, 2, 3, 4, 5, 6, 7, 8 Cl minus at the corners. Hence, the contribution will be 1 for Cl minus from the corners, and then there are 6 at the face centers. Alright, so the contribution will be 3. Total 4 Cl minus in one lattice. Talking about Na plus, what we have is 1, 2, 3. How many edges does a cube have? Because all the edges have the sodium ion. So we know that there are 12 edges and the contribution is 1/4. Alright. So because of the 1/4 contribution from the 12 edges, we get 3. Alright. And then there is one present exactly at the body center, which has 1 contribution, which gives 4 again. So in a unit cell, do not add these two. That will come out to be wrong. Why? Because 1 Na plus and 1 Cl minus makes a formula unit. Do not confuse it with ions differently, because in our unit cells initially we saw only one atoms of the same type. Now here we have 2 different atoms, and these 2 atoms come together to form one formula unit. So hence this is the number of formula units per unit cell. Hence we have 4 Cl minus and 4 Na plus, and the formula unit will be also 4 per unit cell. Okay. Now I will tell you something interesting about this. So if I talk about a isolated sodium chloride unit cell. Now what is an isolated sodium chloride unit cell? If I am able to, in theory, if I am able to take out only one unit cell out of the complete lattice, then what will we see is that because it's only one isolated unit cell, so the contribution will be complete throughout, correct? So what we'll see is that the total number of Cl minus for a isolated, now this has been asked in the exams before, so kindly pay attention. For a isolated Na plus Cl minus unit cell, this thing can't exist. Why? Let us understand that. Because if we isolate a unit cell, the total number of Cl minus ions present in this unit cell comes out to be 14. Whereas when we calculate the number of Na plus ions, you can count them. You can count them here, you can count them at your home too. They come out to be 13, which makes the electrical disbalance. Hence they can't exist. They have to be neutral. A molecule has to be neutral, and here it is not neutral, hence it can't exist. A isolated unit cell just can't exist. Alright. So for the charge is not balanced, so the charge has to be balanced, hence only they can exist together. Alright. Now coming back again to our different types. So next is a zinc blend. Now zinc blend is CCP type, that is simple cubic, right? That is cubic closed packing, simple one. So what we see is that the sulfide ion makes the FCC and the zinc ions make the tetrahedral arrangement around it. Okay. Again the coordination number is 4 and the unit the number of unit cells will be 4. The next are the fluoride and the antifluoride types. Here it's just an opposite kind of thing. So here in the fluoride type, the cations are present, are making a unit cell, whereas in antifluoride it is the anions which are making the unit cell. So this line, you have to note this line down very seriously. You have to take this very seriously. In a question, when they say that A type of atoms make this unit cell, or B type of atoms make this unit cell, then those are the atoms present at the corners. Understood? If I am saying, I'll repeat it again. If I am saying that in a question it occurs to you that A type atoms are making the FCC arrangement or B type atoms are making the FCCP arrangement, then those are the atoms the A type or the B type that are present at the corners and will make the whole structure. And the other type of atoms will be present in the voids and the other places that are left by these arrangements. That is the important thing to note, right? So here we have fluorite arrangement. You can similarly understand by the same concept. So they have 4 each as a number of units formulas in a unit, number of formula units in the unit cell. The coordination number for calcium is 8, whereas for fluoride is 4 in a fluoride structure. In the antifluoride, again you can exactly see the cations are 8 here, and here the anions are 8, whereas in the F minus the anions are 4 here, whereas it's the cations which are 4 here. This is an opposite structure for each other. So this is fluoride, antifluoride. Fluoride में the cations are at the are making the unit cell, whereas antifluoride is the anions. You can remember A, antifluoride for anions making the unit cell, cations are for the fluoride, they are making the unit cells. Understood? Next thing is a very important thing. You will find this wrong in many of these books. So for the cesium chloride, CsCl type structures, many books say that this is a body centered. This is the body centered unit cell. So this is a BCC type arrangement, BCC structure. See, the books will say this is a BCC structure. So the confusion which is created by the books is that it is a BCC arrangement. It is only like BCC and it is not exactly BCC. Can you think of why? Well, because the unit cells that initially we were talking about contains only one type of atom, and here we are talking about ionic crystals. Here they have more than one type of atoms, hence we can't call them BCC unit cell. We can just say that they have a similar arrangement as to BCC. Similarly, they have a arrangement like FCC. They have the arrangement like CCP. Getting my point? So you will find this wrong in many books, and you can correct them too if you want. Thank you. Alright, so coming now, we have talked about the radius ratios and we have talked about the crystals, crystal structures. So let's solve some problems related to that. So let's solve them problems. Here we have read the question, guys. A solid compound contains X, Y and Z atoms. In a cubic lattice with X atoms occupying the corners, Y atoms in the body centered position and Z atoms at the center of faces, the unit cell. What is the empirical formula of the compound? I think it's quite an easy question. What do you say? Let's see how it's solved. So what they are saying is that X is present at corner. So this is basically what is making the unit cell. Because it is present at the corner, its contribution is 1/8. And how many at the corners? 8. So X is 1. Y is present at the body centered position. In the body centered center, so the contribution is 1. But at the body center there can be only one atom. So this is the contribution we are talking about, and this is the number of atoms, and this gives us a total number of atoms that are effectively present in the unit cell. The third is Z. Now Z is present where? Z is present at the center of the faces of the unit cell, right? That is the face center. So how many faces? 6 faces, 6 atoms, but the contribution is only 1/2. So total is 3 atoms. Hence we get the empirical formula to be X, Y, Z, 3. Easy, right? The correct answer is XYZ 3. Clear? Okay, let's see some more questions. Here we have a solid compound XY has a NaCl structure. What it has is NaCl structure. If the radius of the cation is 100 picometer, the radius of the anion will be. Now, what we can understand here is that it has a NaCl type structure. That means that the anions will be present at the corners and the cation will be present at the center. Correct. So, but what we know is that generally the cation is the cation is always smaller than the anion, and here all the anion sizes are bigger, so we can't directly find the answer out. Now, what comes in handy here, what comes important here is knowing the radius ratios. So we are talking about NaCl type structure. Here the radius ratio is in the range of 0.414 to 0.732, right? So what we know is, from this question, we can't directly calculate the answer. What we have to do is, right, that cation ratio is 100 picometer. Now, the cation to anion ratio is in the range of 0.414 to 0.732. Alright. So we'll have to find the answers from both, and obviously since it's a it's a single choice answer, obviously we'll be able to find only one answer which is correct. So what we'll do is we only look at the corners of the range. We'll only look at 0.414 and 0.732 and we'll try to find the answer. Alright, so we are given RC, that is the cation radius of the cation, and we are given the values. We know the values. Alright, we have learned them. Have you learned them? If not, please learn it. It's very important. These values are very important. Kindly learn them. Majorly importantly are these three values for zinc sulfide, for sodium chloride, and for cesium chloride type structures. Yeah, coming back, so what we have to do is we just have to calculate. Now we have this value here and this value, so we can just find the radius of anion. From here the calculation gives me basically this answer. You can check it at your home, no worries, and hence we get 241.5 picometer. Obviously because it's a bigger number, so this will give even a smaller answer, and hence this answer is not present in this answers, and hence we have the right answer here. What happens if there are multiple? Then you have to mark them multiple. Obviously the question papers will be set according to the need of the students, don't worry. Understanding the point here? So the lesson learnt is we have to remember these radius ratios, very important. Okay, let's check some more questions pertaining to the radius ratio only. Now what do we have here? We have KCl, that is potassium chloride, crystallizing the same type of lattice as NaCl. So they both are crystallizing in the same kind of lattice structure that is given to us. Now what they are giving us next is that the sodium ion to chloride ion ratio, and they are giving us a potassium ion to chloride ion ratio. What they are asking from us is the ratio of the sides of the unit cell. They are asking us A1 is to A2, where A is the length of the side of the unit cell. So we need to find the ratio for them. Okay, how would you solve this kind of problem? Now this kind of problem is basically a mathematical one. Let us see how. I think you'll be bored of the red pen. Let us try with the green pen now. So what we are given is Rna plus is to RCl minus. Alright, this problem next thing that we are given is R K plus upon R Cl minus. These two things we are given, and this type of kind of problem is actually mathematical. Why? What we need to calculate is the A 1:A2 ratio, where A is the length of the unit cell, the length of the side of the unit cell of NaCl, and A2 is the length of the side of the unit cell of KCl. Alright, now what we know about the unit cell NaCl type, what we know is it's a FCC kind of arrangement on which the Cl is present at the corners and the Na is present at the center, Na plus at the center of the edge. So these are the Cl minus, and all these three ions are connected to each other. So this length A will be actually equal to twice the radius of the cation plus twice the radius of the anion. Correct? So this A1 we can say is equal to twice radius of Na plus radius of Cl minus upon this A2 will be equal to twice the radius of K plus radius of Cl minus. This is what we have to calculate. Now, can we, from these two quantities that are given to us in the question, here 1 and here's the 2, can now you from these quantities calculate this number by mathematical approach? So what we do is basically add 1 to both of the numbers. You can do this mathematically to these numbers too. What we are doing is adding 0.55 plus 1 and adding 0.74 to 1. Alright, once this is done, what we get here is Rna plus RCl minus upon RCl minus. Correct? And what we get here is RK plus RCl minus upon RCl minus. Now, are you able to reach till here? What if I multiply it by 2? The whole thing. Multiply this also by 2. So 0.55 plus 1 into 2 and 0.74 plus 1 into 2. That's what we have done till now. Simple, right? Next is a simple division of these two to give us the ratio. This will eliminate the denominators and give us the answer. Isn't it a mathematical approach? So from this, the answer actually comes out to be 1.122. Alright, so this is how you have to approach to this kind of questions. You have to solve more and more questions so that you can make a proper approach. Now here there is again a simple question. Radius ratio of an ionic compound is 0.93. The structure of the above ionic compound is of. See, these kind of questions directly come to the exams. If you don't know the radius ratios, you can't reach to the answer. Right? So what they are giving is 0.93. Let us see where the 0.93 lies. The 0.93 lies here, which is a CSCl type structure. Hence the answer is CSCl type structure. Correct? So these are the questions that are generally being asked in the exams. So what you have to remember is radius ratio. That is the takeaway. Okay, so moving forward, next in our line we have defects. You must have learned about the defects. Obviously, defects are of two types, but let us talk about why defects occur. It actually follows from thermodynamics. If you remember that third law of thermodynamics says that a perfect crystal will have zero spontaneity, right? So it will be But what basically the issue with the perfect crystal is that in nature it does not exist. If a perfect crystal would exist, there will be no mobility in the ions, and if there is no mobility in the ions, then there will be no conduction, and then there will be the crystals cannot be used further in different applications. So these defects are actually important. So what we can say from here, what we can learn from here is that in defects lies the importance. Anything that is perfect may be useless too, like a perfect crystal. It is useless. Defects gives it a value. So what we say, we have spots on the moon and it is beautiful. The same is like with the crystals. Alright, so there is no perfect crystal in nature, and that is followed from the third law of thermodynamics. Alright, which says that it will have a zero mobility, whereas there is no structure, no crystal which has a zero mobility, hence the defects are always present. So there are generally two types of defects that we have talked about. One is the Schottky defect and one is the Frankel defect. Alright, so the Schottky defect is basically, so let us just give it with an analogy. Obviously you have learned the definitions very clearly, but I'll just give you the analogy. Like if, let's say, in a school, you're in a school premises and suddenly a kid goes out of the school. Now there is a space left and there is no way to fill that space. That kind of defect is known as a Schottky defect. On the contrary, let's say one kid gets up out of your classroom and goes into another class. Now that kid is not present in this class, but he's left this place and went to the other class, but it's still on the school premise because it is present in the same system, yet only the place is different. This kind of defect is known as a Frankel defect. So Frankel defect is also known as an interstitial defect. How you can learn is basically, I'll give you a proper short trick. So Schottky, right? Schottky contains short means less. So Schottky has lesser atoms, that is atom missing, whereas Frankel is the other one, which is the atoms going into the interstitial spaces and hence showing the defect. Now all the examples are obviously known to you. From the exam point of view, one example which is very important is AgBr, silver bromide. This structure actually shows both kind of defect, that is Schottky as well as Frankel defect. Hence, if you have an exam, these kind of questions where they ask you that AgBr shows which kind of defect, and if it's a multiple answer type question, you have to answer both Schottky and Frankel if it's present in the answers. Alright, so this was more or less about the about solid state. So next we have surface chemistry. This is quite a short chapter. Let us just learn in theory what exactly surface chemistry talks about. So in surface chemistry, what we know is most importantly about colloids. What are colloids basically? So colloids are heterogeneous mixtures. There are two things present in them. That one is dispersed phase. Dispersed phase is the phase that is present in the lower quantity, and this dispersed phase is present in the dispersed medium, which is in the higher quantity. Alright, so they are made up of these two things, make up the colloid. So in colloid, generally the sizes of the particle lies from 1 to 1000 nanometer. The other things are that they show Tyndall effect, they can show Brownian motion, right? And to separate the colloids, which we have studied in your classes, the simplest method is electrophoresis. This is a very important method with which we can actually separate the colloids. Now, the important thing to learn is the classification of colloids. So colloids are classified on basis of different things. Like first is the classification based on interaction of particles between them. So first let's talk about the classification based on interaction between the particles. Based on the interaction, we have lyophilic and lyophobic. So lyophilic are basically, lyo means solvent and philic means love. So the colloids in which the particles love the solvent, right, is known as a lyophilic solvent, colloid, whereas a lyophobic will be that they hate solvent, hence it's called as lyophobic colloid. So the particles try to run away from the solvent in the lyophobic solvent, whereas in the lyophilic they try to attract and be attached to the solvent. For lyophilic the example is gelatin. For lyophobic the example are gold sol or silver sol. Basically any, you can say, organometallic compound salts, alright, silver sol. Okay, now second classification is based on size. Let us look at it on another page. So on based on size, there are three different kind of types. One is macromolecular. As the name suggests, the molecules are huge, big. Hence, the examples are starch, glucose, cellulose, right? So, this is one. Second is multimolecular. Now, multimolecular is quite interesting. What it does is, basically, the particles are actually very small. They can't form colloid, but what the particles do is that they come together. Usually the size has to be in between 1 to 1000 nanometer, and then only they can form colloids, right? And the particles are smaller, they'll form a true solution. So for multimolecular, what happens is the particles actually come together, they become bigger, they show themselves as bigger, and then they form a colloid solution. So for multimolecular, the example is a sulfur sol. Why? Because generally sulfur is present as S8 in the structures. Thirdly is associated. So based on the size, the third one is associated, and the example for these are soaps and detergents. So let us understand what these associated ones are. These are quite interesting examples. So what associated has is that below a certain concentration, they will not act as a colloid. What they will act at as electrolytes, as salts, as ions. At a concentration below a certain level, they act as ions, but at a concentration higher than that level, they start acting as a colloid. So below a certain concentration, they act as a salt or ions. Above that concentration, they act as colloids. Now this line I am talking about is CMC. What is CMC? CMC is critical micellization concentration. Hence the action of micelle formation that we see in the detergents and salts. So yeah, we'll discuss the doubts in a minute. Before that, so here as we can see, CMC is critical micellization concentration. So above this concentration only colloids are formed. Below this concentration, they act as a ion. This associated colloids, they act as ions. They remain as electrolytes in the solution. Where as soon as the concentration rises above the CMC, they form colloid. So same action when we see how the dirt is removed with the help of detergents and soaps. So what happens is basically with the dirt, they form micelles and colloids. Hence they remove that dirt, right? So that's the example for the soaps and detergents. Kindly remember associated colloids. Alright. Lastly, one more thing, Hardy-Schulze rule. You must have heard about it. So before that, let me talk about some important terms which are related to surface chemistry. So surface chemistry generally has terms like coagulation and flocculation and peptization. So these terms are quite important in surface chemistry. Let us understand what the meaning is. So coagulation or flocculation basically means breaking of the colloids, whereas peptization means making of the colloids. Alright, when the colloids are formed, that is known as peptization, whereas when the colloids break down, that is known as coagulation, or that is known as flocculation. These terms are quite important as they are directly given in the questions, and the students are not able to answer just because they don't know the terms. So remember, if next time in the question they say that the colloid is flocculating or coagulating, that means it's breaking down. Whereas if there is a term called peptization, then it shows the formation of colloids. So if you want to calculate the coagulation power, what do we see? What do we find is we can do it by Hardy-Schulze rule. So what does Hardy-Schulze rule say? So if we have two same type of compounds, AlCl3 and NaCl, forming salts, we have two different type of compounds forming colloids. If they form colloids, then what is their coagulating power? So what Hardy-Schulze rules say is the coagulating power depends upon the charge of the uncommon ion present in the compounds, in the substances forming the colloids. So here the uncommon ion is Al and Na, correct? The charge on Al is 3+, whereas the charge on Na is plus. Hence the coagulating power will be more for AlCl3. So greater the charge, more is the coagulating power. So this is what is Hardy-Schulze rule. Okay, let us see one more example. Here this time we have sodium acetate and sodium phosphate. Now charge, here we have sodium as a common ion, so anion, we will be talking about the anions here. So we have CH3CO minus, that is -1, and PO4S 3 minus. So this time here this will have more coagulating power. Alright, so this was all about the surface chemistry. So talking about some questions, this question is a doubt asked by Atharva. So the question is basically, sodium at body center in sodium chloride is not connected to the corner Cl minus. No, I'll explain it with the structure again for you. Now kindly understand the structure very nicely. Here I am making just one unit cell. Alright, now I'll make similar unit cells across this. There is one more unit cell. Now there is one more behind, and then there are 4 on the top. Are you able to imagine? Here. Right. So this here was the center. Now so here this Cl minus will be connected to only the NAs, which will be here. Okay, I'll make it with the red pen. The Cl minus at the corner will be connected to the 6 which are here. Here 2, this is 3, this is 4, this is 5, and this is 6. So what your question basically is, the Na, the sodium present, is not connected to the corner. Yes, you're correct. So the sodium ion which is present exactly at the body center will not be connected to the chloride ions which are at the corners. Only the ones that are at the edge centers will be connected directly to the ones at the corners. Alright, so the sodium ions which are present at the edges are directly touching, and hence they are the ones that are giving the coordination number to the chloride. So hence 6 for the Cl minus and 6 for the Na plus. The sodium ions present at the body center will not touch the chloride ions present at the corner. Any more questions? Okay, thank you very much for your response. Bye bye, see you soon with next fun class.